Okay, so first of all, good morning to everybody. And what I'm going to talk about is quantum heat engines. This is what I was assigned for by Nicole. And what's nice about it gives you a certain perspective on thermodynamics, on quantum thermodynamics. And in a way, this is a tradition of thermodynamics that you learn by example. You take something, you try to figure it out, and then you generalize. So this is the spirit of thermodynamics, which kind of, in my, how I look at it, carries out also to quantum thermodynamics. And so I won't be able to cover all what I prepared for you. And my lecture notes are in PDF, which I'm going to show you here. I'm not going to go all through all of it, but it will be posted on the webpage. So I already sent them in, so hopefully they'll appear. So you don't have to write too much. You can ask questions. I'm not going to go through 140 pages that they prepared for you, so you can read them before you fall asleep. So my first lecture will be on quantum discrete heat engines. And so I start with Carnot autocycles. And just to say something about Carnot, Sidi Carnot was an engineer in the French army, and his father supported Napoleon. So he was after that, and he was, since his father supported Napoleon, he was a no bad guy from the point of the French army. So they sent him to some fort to rebuild it or fix it or something like that. Anyway, so he'll be away from Paris from any trouble. So what he did there, he wrote a book, and it's very analytical. He didn't, from the point of view of Carnot, unlike the British, which were building heat engines, he was really thinking how, it's in a nice French tradition, how this should work. And you should think it's very original work because he had no notion of energy and entropy. He didn't have these concepts. They were built after his work. So what he had is a kind of obscure concept, which is called calorie, which is hard to translate what he really meant, but he got things right. And the way he got things right by thinking analytically, and basically, you could say the Carnot engine is its construction, and you can learn a great deal from that. So what I want to continue to quantum thermodynamics is always a question: how small an engine can be? Is there a limit to thermodynamics? How far can we push it? And when you think about steam engines, macroscopic things, you think that things are huge. And the answer is there's no limit. You can go to one particle and you can apply the principles of thermodynamics, and you can build a machine with one particle, and Ferdinand did that. So at least I have one witness that built a machine with a single particle. So thermodynamics works from basic microscopic to macroscopic systems. So we have a unifying theory that covers everything. And to give another perspective, we were talking about Einstein. Einstein, in his 1905 paper, started quantum mechanics by considering thermodynamics. If you read the paper, what he does there, he calculates the thermodynamics of light inside the box. You can see the entropy of light inside the box, and then he reaches the conclusion that the only way he can explain it, since the entropy is the same as the entropy of the particle in the box, so then the only way you can explain it by quantizing light. So you could say quantum mechanics started from thermodynamics. What we do now, since, as Nicole says, nobody remembers thermodynamics, we do the opposite. We start from quantum mechanics and try to derive our thermodynamic principles. Okay. So let's start. Okay, we could go here. We can start with an engine. So we're going to do both Otto and Carnot engine. And maybe before I do that, Here, move this a little bit up. Here, this is what I want. Let's use this as a pointer. Okay, so what do we have here? We said we have our four-stroke engine. We have a four-stroke engine. So you can say, what are our strokes? This is like our engine. So I have hot bath thermalization. I have a heat source. So I thermalize with my heat source. I do a unitary expansion from hot to cold, or in thermodynamics, you could call it adiabatic. Word adiabatic I don't want to use because it's overused, so it's used in many contexts. And you can say there's cold bath thermalization and a unitary compression from cold to hot. So this is a four-cycle engine, and we'll do it different ways. And you can see the difference between the Carnot and Otto cycle, that when you do this unitary expansion in the Carnot engine, you're connected to the heat bath. You do this, when you do this thermalization, you're connected, you're both and the heat at the same time. And same thing here. And then Otto cycle, you could say is what's called isochoric. You separate the heat transport from the, say, the work transport, and it makes the analysis much easier. That's why when you look at the literature, you see that 99% of the papers do Otto cycle and very few do Carnot because it's more complicated. Carnot is way more interesting, so we'll do both. Now, when we look at it like that, we can say, okay, what do we need to describe in a theoretical way an engine? We need a propagator to move the state from one place to close the cycle. And we can say we have a propagator of the cycle, which is composed of a concatenation of all the stroke cycles. We have strokes and we have an overall cycle. So you can always write an engine like that. And when we think about things and we look for a fixed point of this snap. Because we want to know if I start my car in the morning, it does a little bit, and then settles to a fixed point. Goes through the cycle and repeats itself and it's periodic. So this is what we're looking at. And then there's another important issue. Yeah. Okay. So now we have both Carnot, also both Carnot engine and Otto engine. And I'll choose a Hamiltonian to make it more simple. So I'm putting an engine with a qubit. Didn't you use it out of head? One of your right or red. So you can tell my engine is composed of a single spin. So SD, my spin operator, my angular momentum operator. And what I'm doing, I'm changing frequencies. So you can think of my engine as some spin. I'm changing magnetic field, and I can perform with this. You can say both Carnot engine and single spin Carnot engine or multiple. So the cycle goes, as we said, through thermalization and work moves, which I'm changing frequency. And we can look at it over here. So what I'm showing you here, this axis is polarization, the difference in population between up level and down level. And this axis here is the frequency that I'm going to change. So what do I see here? The blue line is called the cold isotherm. So that means that my spin is in equilibrium with a bath at temperature Tc. So you can calculate that if you want the polarization as a function of temperature. If you want to, so that's a hyperbolic tangents of h bar omega divided by kT. So this would give you this curve here for the cold bath, and this will give you the polarization for the hot bath. And you can see when the frequency is 0, we get the degeneracy point. So these are the limits of our engine. And how do we work the engine? Engine works by moving heat from the hot side to the cold side and using this, you can say, this current to produce work. So Carnot engine, let's say, starts from here from omega 1. We start from this point. We equilibrate. So you can say we move population into the excited state. So we go up in polarization. And then we move according to this line. So the polarization stays constant. As Nicole said, that means that there's no entropy change because the population is constant. We reach this point. We go to move to here, point number 4, and we close the cycle. So this will be a Carnot cycle. And an auto cycle is this square here that we do here. So you can say we start from this frequency here, we move here, and we close the cycle like that. So these are called isocores, which means the volume is constant, but in this case, our frequency is constant. And now you can immediately see what I would call a geometric interpretation. You can say, okay, what is, you can say the area here is what I can get out of this engine. And you can say this, if I look at this, efficiency is this area here divided by this area here. And for the auto engine, it's this area here divided by what's going on here. Okay, so what did Carnot teach us? That if the engine works at equilibrium, there is no entropy change during the cycle. So the amount of entropy that they get on the hot side should be the same as the amount of entropy change that they get on the cold side. And the entropy change is only in the bath. So I can write it like that. Let's say the entropy change at the hot side will be the amount of heat QH divided by TH. And the cold side should be blue. Right? No, only black. There. And what we said that these two are equal. So from this we get zero. So we can say that the ratio of heat is the same as the ratio of the hot side to the cold side. And from this, I let you get into the exercise that you can get the efficiency, which is the work divided by Q. And what is the work here? Since there's conservation of energy, it's a difference in the heat that I get from the hot side to the heat I expose on the cold side. And you immediately get from this what omega is heat. So all what I did, well, you could say, into Carnot, assumed equilibrium. There's no entropy generation. And you look what the engine performs, and you get the Carnot efficiency out. And if you want to calculate the work, write it here. The work is KT delta T times delta X. You see, it's the, if I would plot it on the temperature entropy, it would be the area of the rectangle. So this is the difference in entropy, this is the difference in depth. So this gives me the work for the Carnot set. So you could say this is very classical, although you could say it's a discrete energy level system. So it's a quantum or classical. So we get the classical result on that. Okay, so what? The auto engine. The auto engine, you can say we're using this smaller rectangle. And what is the, you can say the efficiency here. So you can say, I can immediately get this out of these areas because it's very easy to calculate. So you can say, I see here, this is delta omega divided by the hot, this one, the hot side. So my efficiency becomes, as I said, delta omega divided by the hot side. So the efficiency for the auto engine is also kind of very something you see a lot. 1 minus omega c divided by delta omega divided by omega h, and you get this stuff. So immediately you can see the efficiency is lower than Carnot. On the other hand, from this point of view, if you only think about efficiency, you want to be Carnot, but you don't want to be there. And the reason is, if I buy a car, I want the Lamborghini, I want power. And Carnot engine works with zero power, and now we have to go to the next stage, and we want to think about engines that produce power, means work per unit time. And this is what we're interested in. And this brings us here to this picture, which is what's called another subfield, which is called finite time thermodynamics, which means a trade-off. And I think Lenny will talk about more trade-off. This trade-off is a trade-off between efficiency and power. And this trade-off here, which we do under Carnot, is called the endo-reversible limit, or the endo-reversible model. And the idea is that I'm going to sacrifice efficiency for power. And how do I do that? You can say I have an inner engine. You can see an inner isotherm, which is embedded inside the outer one. Why do I need that? Because I need heat to flow into the engine, and I need heat to flow outside the engine. So how do you get a heat gradient? You have a different temperature between the temperature of your working medium, in this case is our spin, and the bed. So then I have a finite heat flow. So if I want a larger heat flow, I'll have this temperature difference larger. If I'll have a small, and if it will be zero, then it will be again equilibrium. So you can see that I'm sacrificing efficiency because now I'm working this internal engine here, which is called the endo-reversible engine, and sacrificing efficiency for power. And you immediately see from this picture that eventually, if I do too much, I'll get nothing, because this area in the middle will collapse and they won't get anything out of it. So this limit is called the endo-reversible limit. You see there's a heat gradient towards the engine and outside the engine. And you can see the inner part is reversible in this model. And I sacrifice this heat transfer. And this idea started when people started nuclear heat engines. There's a first mention of this type of model, it's Novico. And then it was redone, and today it's called, typically called the Coulson-Algol efficiency, which is a nice paper in American Journal of Physics. And again, it has been rederived many times. And if you do this for this model, you get another efficiency, which I'll write here. Blue.
Your favorite color.
I got blue, but I'll now use, if I got blue, I'll use it. Here, so this is another efficiency, which is called Coulson-Algol, which equal 1 minus the square root . And in order to get this, so it's a high temperature limit for, if I talk about spin, here, you don't see it here, but it's somewhere. So if I talk about spin, this result will be a high temperature limit. And the low temperature is more complex, but it's a very good thumb rule. And if you look at it and you ask, okay, how much efficiency I have to sacrifice to get to maximum power, or how much power, how much you can say work I got less. So you say I typically get half. If you want to know what's a thumb rule, so I get half the work that I would get in the reversible case. This is the leading order in an expansion also. So this is a very good sum. You get half. And if you take this Coulson-Algol efficiency for typical power plants around here or wherever, it gives a good number within a few percent. So it's a much better estimate than Carnot engine for things that we want to work at finite. So we added here something that already you didn't ask about. I'm out of equilibrium. I have heat transfer. So I added to my theory something that's already outside the typical classical thermodynamics in order to do this. But you could say the original paper of Coulson-Algol used Newton's heat transfer law. So you can say that's an empirical law. And in a way, what we want to do is go beyond that. Let's look at this. And more quantum in this sense. Okay, so now let's do an Otto cycle. Here's an Otto cycle. So what do I do? I have another one. Oh, so this, my pointer doesn't work, so we'll have to pull this up. So you can see I have an Otto cycle. And the extreme cases, you can say I reach equilibrium, means at each end of the, let's say, thermalization stroke, I reach equilibrium with a hot side, and then I reach equilibrium with a cold side. But this, again, will take infinite amount of time. So I'm going to sacrifice, again, my efficiency for power. But you can see the efficiency doesn't change. You can see if you look at the yellow rectangle inside this auto engine, it has the same efficiency. Because the efficiency is always 1 minus omega c divided by omega h, if you look at it like that. So I didn't change my efficiency, but I get less power because my area, the yellow area is less than the green area, so I get less power in this case. But you could say I get it in finite time because I have heat transport. So you say don't go all the way to equilibrium, and I not on the hot side and not on the cold side. So this internal rectangle is what's going to be my auto engine. And now I have to assume something. How much time will it take to do the diabatic moves or the unitary moves? And the assumption is, in this case, that it will take, I can do it as fast as I want. So I can move from, you could say, move my frequency from omega 4 to omega 2 as fast as I want. So if I do that, then you can ask, okay, I want to optimize this engine. I want to get the maximum power out of it. What do I get? Which solution would I get out of that? So you could say, I have to, in a way, optimize this yellow rectangle in order to get maximum power out. So what is your guess? What is the solution is the best thing to do? How we have typically intuition about optimization. We optimize all the time. So what would your guess be in this case? Nobody has a guess. Okay, it's good because I got it wrong. It's a bang-bang solution. You do like that. You could say for stroke time becomes infinitely short. What you do, you touch the hot side, you get a tiny bit of heat, you go back to the cold side, you dissipate a tiny bit of heat, and you do it as fast as you can. So you get a cycle that has 0 time, because you do it like that very fast. It's what's called a bang-bang solution. And this is typical for optimizations that we find in quantum mechanics, bang-bang solutions. And that gives the maximum efficiency. And again, how much power do I get? Half. That I would get in the... So you could say per cycle, the amount of work is 0, but since my cycle time is 0, you divide it and do the limit, you get half the power that I would get, half the work that I would get in the green cycle. And this is the, let's say, the optimal auto cycle. Now, when we got this result, I said, okay, this is wrong. Why is it wrong? Physically, you can't think about something that goes so fast. You have to do something. What's missing here? Why isn't my car going through extremely RPM, if you want? There's something missing in my picture here. What is missing? What do you know? What is a source of irreversibility? I did heat transport. What is missing? Friction. Friction is missing in this model. So if I put friction, you know I can't move my piston infinitely fast. Typically, friction is inversely proportional to velocity. That would set a finite cycle time, and then I would get this optimization solution wouldn't be correct. Okay, so now, after we have, I would say, an introduction, which is almost fast. Let's say, except discrete energy levels, I didn't say really anything for quantum here, except I wrote a Hamiltonian. So in order to get both heat transport and friction in a quantum setting, we have to go beyond what I have here. And this is my next chapter, which is, why doesn't this? You know why this doesn't work?
What does it?
The pointer.
Oh, battery is right.
Maybe it's off. Yeah, very simple for the button.
Is the spin assumed to be a 2-level spin, or is it a more general spin in this case?
Okay, you could say this would be as any SU2 would work. You want the minimum model would be single spin that you could have any SE2 would be given exactly the same. So that's why I wrote it as Z, not sigmas. Yeah. Okay, so what is this? Now, is there any analysis? So I'm going to talk about the dynamics of quantum thermodynamics. We're going to go out of equilibrium. That answers the question. Our quantum thermodynamics is out of equilibrium, and we need a description. And there's an echo, but never mind. So what we need is really the theory of open quantum systems. And this is what we need to do that. And with certain modifications, because the theory of open quantum systems is not sufficient.
It says your sharing is paused.
For what we need. So I'm going to create a few basic concepts that I need in order to describe a real quantum engine. And what we need is this screen. Something happened here?
Well, it says your sharing is paused again. I don't know what.
I don't know what's happening.
Maybe you have to restart the sharing. It says shared is like this. So maybe you stop and then restart it.
Stop again, start again.
Start in the sharing part of it, yeah.
Okay. So I hope you know, I'm going to go through this relatively fast, but if I'm going too fast, just tell me. So I need certain concepts, otherwise I can't analyze anything. And my first concept is the von Neumann entropy that we need. So as we said, if we start from Carnot, we need entropy. That's our guide, not energy, it's really entropy. And von Neumann entropy is this construct here. And you can ask, is it measurable? The answer is no. It's an abstract thing that is very useful, but it's not directly measured. And if I give you a system and you want to know what's von Neumann entropy, and they don't cover anything, and you're allowed to do measurements. So what you have to do many types of measurements, and you want to find the measurements that will give you minimum dispersion, and that will give you the von Neumann entropy. So it really, if you want to really determine that, gives you a lot of. But anyway, what's important about the von Neumann entropy, it's invariant under unitary transformations. So if I do a unitary transformation, like I did my stroke, the von Neumann entropy doesn't change. Okay, so this is one thing that I'm going to use. The other one is this trivial statement that the function of a Hamiltonian commutes with the Hamiltonian. And I can define another type of entropy, which I call the energy entropy. And that is if I do a complete measurement of energy, get my Hamiltonian, I get a discrete system, I get the probabilities on all states, I can calculate the Shannon entropy of my outcome, and you get the energy entropy of it. You can see that these P's are the expectation values of the projections. Now, since this is a function of energy, again, it commutes with the Hamiltonian, and it doesn't change if I do dynamics driven by this Hamiltonian. So if my unitary is driven by a Hamiltonian, the energy entropy is also an invariant, a constant of motion. So I have two constants of motion. You can see the von Neumann entropy and the energy entropy. And you can see the energy entropy is always larger than the von Neumann entropy. Von Neumann is the minimum entropy of all possible measurements. And now I can define a new construct, which I would use to define coherence. And this is what we need to do quantum mechanics. And my coherence is the distance you can see between a density operator in general, and if I only take its diagonal and the energy representation. So this is sometimes called the relative entropy or the pull-up divergence. And if you do that, you can see immediately that it's a difference between the energy entropy and the Boltzmann entropy. So I can use this to quantify how much coherence I have in the state. So if my state is in equilibrium, so the energy entropy and the Boltzmann entropy is the same, I can say my state is in the energy free. If not, I have coherence. And so now you can say, oh, if I do unitary transformations, then we can see, okay, what does it mean? Why do I need this definition? I want to know if it costs me to generate entropy. And you can analyze this expression, which we'll do in a minute, and we will see that in order to, if I want to generate coherence, I have to kind of break this, what happens here. So how can I break it? If my Hamiltonian is time dependent, then this won't be correct. This would still be correct, and then I can change my energy entropy, and I won't change my volume. So what we can see from this, from these definitions.
So far, everything is defined in the system for the space.
You can say this is completely general. I have a Hamiltonian of my whole system. Now I'll start to partition. So you can say that, and your question is very good, because this is the viewpoint of quantum thermodynamics, at least a partial viewpoint, and I have a lot of arguments with my friends about it. And the viewpoint is called sometimes the church of the larger Hilbert space, which means that we assume that the universe is driven by a Hamiltonian dynamics. So we have a Hamiltonian, and then on the universe, we have our conservation laws. So this is a symmetry. So we impose a symmetry on the universe. Is it true? We don't know. That's what we call the church. So you can say, I'm a believer in this church. In general, believe too much. But maybe this church I can buy. So you can say, at this point, we're talking general. We have a Hamiltonian. Now we'll start to partition. So this is the point of thermodynamics, we partition. And I would say there's another point that you're saying, that thermodynamics is a lot about idealizations. What I say is not strictly correct always. Like an ideal gas, there's no gas which is an ideal gas, but we know it's a good concept to try to understand. So when we do, it's our quantum thermodynamics, we also do idealizations which I'll use. And I know they're not always correct, but it leads me to certain limits or things that I can really do construction. So you can say my next step will be to partition.
Now, do you find this definition of coherence significantly more useful for your purposes than just the sum of all the off-diagonal matrix elements, density matrix?
Okay, this is thermodynamically, this is very useful because it's all in the concept that we use entropy. And you can say the Kosloff distance is a very useful concept, also in quantum information. So I would say this is very useful. Now, there are other, if I can take you can take the square of the off-diagonal elements. This is another, it's another metric. And sometimes it's equivalent and sometimes not. But this, you could say, you could ask, let's say I ask the following question. I give you a system in thermal equilibrium. And I want to generate the maximum coherence. How much will it cost me? The maximum coherence in this system. So what does it mean? It means that I have to in a way, as I said, since I'm going to do it by a unitary operator, I'm not going to change the von Neumann. The von Neumann, the initial one is fixed. It's just a diagonal, right? So I'm going to fix, I want to maximize my energy entry. What will that be? Microcanonical distribution, right? That all the diagonal elements are the same. This would be the maximum that I can do for energy entropy. And immediately that answers your question, how much work I have to put into it. It's a difference for energy. It's a difference in energy between a canonical distribution and a microcanonical distribution in the same system. So that's, you can see that's why I think this is a very useful concept. It at least gives me a limit. Okay, this is the maximum coherence I want to generate, how much it will cost. You could ask it differently. You can say, if I have a fixed amount of energy, what's the maximum coherence I can generate? And I already answered your question, because I'm going to change from one canonical distribution to another one which has a larger energy, right? It's also going to be canonical because that's a maximum entropy. And you can see the difference in energy. This is going to give how much coherence it can buy. So
Your choice of basis to describe.
no, the basis is always energy. Coherence, from my point of view, is always defined with respect to energy. I know there are definitions with respect to other bases, but that doesn't make sense. And the reason is that you can say the Hamiltonian is invariant. And this is the concept I use. So coherence really means I have something transient. It's going to change in time. So these are off-diagonal elements in the energy representation. Otherwise, it's dead, static. So that's why the preferred basis is always energy for coherence. Now, people use others, but then you really have to justify why. I don't have to justify. I gave you kind of a hand-waving rule, which allows you to calculate a very important issue. You can say that to generate coherence costs energy. And since it's unitary, it's reciprocal, if I have coherence, I can get energy out of it. So it means I can get coherence, I can translate it back to work. So if you have a source of coherence, I can get work out. And we'll see later that this is really the distinction between what's quantum energy engine, which has coherence, and a classical engine, which is semi-equilibrium, it's all population.
If I have a Hamiltonian which has a SX term in addition, and I can switch from, switch or make S3 into SX back and forth, then you can create.
Yeah, you switch Hamiltonian to the right, sure.
Yeah.
So I can think about it, 90% or something. It doesn't fit. So the commutation relations tell everything. If I add a new Hamiltonian, it doesn't commute with the first one.
Yes.
You're going to generate coherence. Okay.
That was exactly what I wanted to say. Like if you change the basis in time, you have to count that in your equation, right?
Yeah, so if you, okay, what happens when you have to change the basis in time? So I'll go back to that. So in general, I'm going to stay with energy. And it's a good question, and when I'll analyze an engine, which I'm changing the Hamiltonian in time, I'll answer that. And the general answer is the same. There's energy, that's my primary. Everything that doesn't commute with energy is going to be coherence. So if I change my Hamiltonian, I follow my energy.
That's so your definition of coherence changes.
Yeah, I would say the definition doesn't change because it's always, I always put my density operator in the energy. You can say. Now, I'm going to go to it now. There is a thermodynamic justification for that. So you could do anything in quantum mechanics if you're consistent. You could say it was Hilbert space. The thermodynamics puts additional restrictions. doesn't allow you to do everything. And then you can say energy becomes a primary object. Okay, so I'm not going to use a few definitions here, which you know. Well, that we're talking about density operators, and I see nobody objects to it, so that's at least. And as I said, this is the composite dynamics is driven by a unitary. So we say that density operator is driven by a unitary operator that you can write it like that, and I'll use this notation, this scribble U to describe the unitary evolution of the universe in this case. So I have a Hamiltonian driving my total density matrix of the system. And here, and the unitary is generated by the Hamiltonian, so I call the Hamiltonian the generator of the dynamics. And so you can say this is the unitary and it's generated. So these are, you can say, general quantum mechanical definitions. I didn't do anything to modify them. Verse 3. Okay. Now I start to do what you asked me for, is partition. So this is a serious issue. Which starts with idealization. Now, I have system A and system B, and I have Hamiltonian A and Hamiltonian B. And I have a total Hamiltonian of HA plus HB, and I have an interface. So what we want from thermodynamics, at least, we want something that resembles what we call an isothermal partition. That allows transport of energy and keeps the systems intact. So I can describe system A and I describe system B, and I have a flow across the interface. Now, this is, I would say this is what I want. I want to keep the integrity of the system. And immediately, when you think about it, I have problems of entanglement and all kinds of other things. But we want to keep it as simple as possible. So we say, I put this partition, and in the thermodynamic limit, this is volume, this is surface area. You ignore the surface area. So I want to do the same thing. What I want to claim is something weaker, that there's no energy accumulated on the interface. The energy that leaves system A goes to B, and when B goes back to A. So this is going to be my equivalent of an isothermal partition. My partition doesn't accumulate energy, and it means that I can understand energy transfer, either it's here or here. The total energy is conserved because I have to. But this term here doesn't accumulate. So what does it mean? If this term doesn't accumulate energy, it's a constant. It means it's an invariant. So it should immediate consequence that HAB should commute with H. Doesn't change by the dynamics. But if it commutes with H, also commutes with HA plus HB. So also, you also can write that HA plus HB commutes with the global temperature. All these are conserved quantities. So I put, this is a restriction. I put the symmetry, this is called a dynamical symmetry, into my construction. And I say, okay, this is the origin of this is not mathematical, it's physical. This is my ideal thermodynamic set. So once I do that, here it's written here. Okay, so this setting here, if I look at 5, setting 5, I can extend this and say, okay, HB is my bed. And you can put another setting because what my ultimate goal is to get dynamical equations of motion. And I can say my environment is infinite and constant temperature in a canonical distribution. So I don't have to have this number 5, but if I want to make progress, and what I want to get to is what's called a reduced description, equations of motion for my system only, I need to assume something about my environment. B is going to be my bath. My bath is infinite. It means its temperature won't change if energy goes in and out. But then I can calculate the entropy very simply, how much heat divided by the temperature. And okay, so this is going to be my setup. And then there is something that Nicole started, and really is, there are subtleties of definition of heat and work. And there are a lot of subtleties that I won't go into anything. And the problem is that once you put a time-dependent Hamiltonian into your problem, you immediately assume a semi-classical approximation, something that drives my Hamiltonian time-dependently. So what do you do about it? Because you want to start your definition from something as clean as possible. And since we started to talk about partitions, so we add a battery. So our partition is here, I have my controller or a battery or whatever you want. Here's my system, and here's the environment. So I can have a setup like this. So this external controller drives my system, and it's coupled to an environment, as we said, with the temperature. So this is one type of setup. And I can also think about it like that. I have these two things form a larger system that's coupled to the environment. So you can say also my controller feels the influence of the environment. And these are two types of partitions, and they'll give different definitions of heat and work, depending on which symmetry you choose. And this typically is better for quantum optics. This is for other systems. This is partition. It's more, makes more sense. But it depends on what you do. And the question of getting partition is an idealization. Okay, so what do you do in this type of partition? I say I want to put, this is a controller, so it's driving my system. And we said something about the environment. The environment we said is stationary. We said it's in a thermal state, so it's stationary. My environment is in a way something dead, doesn't move. It absorbs and emits energy, but that itself doesn't change. But if the controller would be like that, it would be an environment, so it would be useless. So what does it mean? That this has to have coherence. This can't be stationary. So my environment has to have coherence, which is going to drive my system. And everything is, you can say in this case, my system is coupled to the environment. And my ultimate goal here is to get dynamical equations of motion for something like that. And in this fashion, I can get, let's say, model my Kosloff engine, which eventually that's what we want to do. So I can do it like that, or I can do it in this type of partition. So the time dependence is hidden here in my controller. So what does it do? This is something that's typical in quantum field theory. You put the time dependence in initial conditions. I put coherence here. Once I put coherence here, then there'll be something happening because it will drive my system. So I'm out of equilibrium situation. The coherence here will drive my system. And what did we see before? Coherence in a global environment is a constant of motion. Because we said the von Neumann entropy doesn't change by the total Hamiltonian, and the energy entropy doesn't change by the global Hamiltonian. So you could say, if I look at everything together, coherence is another dynamical system. It's conserved. So what can I do with coherence? I can transfer it. So I started with coherence here, and I can transfer it to my system and get rid of it, basically dissipate it in the environment.
Are we assuming the same condition for AC in addition to the system in that?
I have to put, yeah, so I added another partition.
Yeah.
So I added another system. You can see what they did here. If this is my system in that, added my control. So after this AC instead, couple. That's just so I have transferred to this. And again, I added that partition. So you can see the general assumption that these are described. This system, this system, this system. And what I do, I transfer coherence from here to here, so I drive my system, then I dissipate it.
And the constraint is that HAC commutes with the total.
Okay, that depends on the partition. You can see in this case, this square root, this square commutes with the total Hamiltonian. So the interface here commutes with the total Hamiltonian. And in this case here, you can see, so I have both conservation of energy here. So you can see that's why you get different definition of heat and work, because I changed my partition. So the partition is what makes thermodynamics, the partition of the system. And so this is a change in the system. Okay, so what you do, so this is a very general setting. And in order to get something that you want to work with, which is a time-dependent Hamiltonian, typically what you do when you start from here, you go to the semi-classical limit, and then you can get a description within with a time-dependent Hamiltonian, but you know at least where you started. I started with something that's completely, you could say my Hamiltonian is time-independent. All the time dependence is in initial conditions that live inside my control.
Okay.
So the next concept that I need, and here I threw away, I threw away the controller, so we'll go back to that, is here I have system, environment, and coupling. And the next construction is what's called the reduced description. I want to get the map that moves my system in time. So the map is like that. So it takes my system from time 0 to time t. And since we assumed dynamics by general Hamiltonian, we can write it like that. It's a reduced description. I take the trace over the path on the unitary, and there is an assumption here that at time equals 0, the system and path were uncoupled. And I emphasize this because this is one of the things in quantum thermodynamics that people argue about, and it's not clear if this is correct. because this means that at a certain time, when I was born, I was separated from the environment. I don't believe that, but could be. Anyway, this is assumption that we live with. And you can say all the theory, that useful theory is based on it, very hard to get rid of this assumption. And what it allows us to get is what's called a reduced description of this map. And now this is what is called standard. Go through this divergence first. And what is standard, but if you look at this inequality of the divergence between two density operators, this is a paper of Lindblad from 1974. And what Lindblad was able to prove that this dynamical map is a reduced description, or what we'll refer later what's called Krauss form. This is always contraction. So it means I have two density operators and I apply on both of them this dynamical map, the distance between them becomes small. So this is a contraction property of these dynamical maps. You can see the information, where is it lost into the environment. And then if one of them is in equilibrium state, then it means that if I apply a dynamical map that will reach the fixed point of the dynamical map, then monotonically I'll approach equilibrium. So if I apply the map again and again and again, eventually the distance will become smaller and smaller and smaller. And by Cauchy's theorem, we have series that is bounded and becomes smaller, I'll approach equilibrium. So you can say this tells us something that we expect from thermodynamics, that if we have a dynamical map and we apply it many times, we'll reach the fixed point of the map, it's invariant, and we'll reach equilibrium. These maps are called completely positive trace preserving, or Krauss map. And this is a construction that we use for open quantum systems. And this is what they're going to use. Okay. Now, I'm going to use something I won't prove, but I put it here as a theorem, which comes out from what I wrote here, which is erased. I'll write it again. Have my system, I'll write it in this notation, environment, H is E, then H system plus environment. Newton's H. Then we can prove an important statement, which is again a symmetry statement that tells us that here, this is what I told you before. Now I can take the unitary evolution of my system under my system Hamiltonian, which is this. And I can define what's called free propagation. So I took my system, that's in my spin, it's Hamiltonian, that's its omega z, it has free propagation, and that defines a map, also a unitary map. And then I can have the general map, which includes the environment, which we described by this lambda here. And what I claim that if this property exists, these maps commute. So you can say the free propagation, and you can say the full propagation, which includes the environment, commute with each other. The maps commute, and this is a consequence of the symmetry. So the symmetry, you can derive this. It's a little bit technical because you have to go through the reduced description, and you get this commutation relation. So it's a language of symmetry. What is this type of symmetry? You can say free propagation is a clock. Tells me what happened during time. So if I look at my spin and it propagates, you can say if it's in the X direction, it's like a clock that evolves. It accumulates space, so I know the time. So what this tells you that if this clock commutes with the environment, I can't use the environment as a clock. The environment is different. Doesn't matter when I approach it. It's always going to dissipate. So if I approach my environment today or tomorrow, it's going to behave in the same way. So this is, you could say again, an idealization that I can't use my environment to measure time or to have a time reference. So sometimes it's called phase covariance. This is a more technical, and this is a consequence of the symmetry, you can say, of this partition. So we're going to use this. We want equations of motion that obey this relation, which are, you could say that will be thermodynamically correct. So I need to keep this construction. So this is what we want. So we can write that if you want. It's a commutator, but it's a more, when do we have to finish?
Oh, it's up to you entirely, but I suspect you don't want to use all 45 pages.
No, I have 110 page. But you, so what's the time? You should just tell me when should I stop.
Choose a natural break point.
Okay,
Yeah,
that's what I assume. Okay, so if you get this idea, that's enough for today, as I said. So all our equations, which are thermodynamically consistent, will be based on this dynamical symmetry. Eventually, what we want to get was a master equation. This is what we want. So we want our master equation to be like that. Now, these are abstract things. I'm talking about maps. So what? It's an abstract Hilbert space. It's a Hilbert space of operators. This is the language we talk here. But you think about operations, you know what you're doing. I'm moving things from here to here, I do something. So a map takes my system, moves it around, and you can think about that. And what, under this framework, we can do many things. I'll do maybe a little bit more. Yeah. I'll just reach to this point here. Okay. So what we want to move from the map, we want to get equations of motion. A map is not an equation of motion, that's an integral. So to get equations of motion, I basically have to derive the generator of the map. And here, the generator of the map we call the Liouvillean. And I'll just write the definition here. This is my dynamical map. And I assume that I can write my dynamical map like that, static. And it's a little bit more subtle than that. I should use this definition. This is better. Because if it's time dependent, I'll use this. If it's time independent, I can use this definition. Of the generator of my dynamical map, it's called the Liouvillean. And you can say that the seminal work of Gurini, Kusakowski, Sudarshan, and Lindblad, that it has this structure. L has to have this structure. It has a Hamiltonian part and a dissipative part, and the dissipative part will have this structure. And this is, you could say, more general than Markovian. Although the original derivation was for Markovian dynamics, this is more general than Markovian dynamics, what it requires is what's written here, that my map has an inverse. If my map has an inverse, I can write it in this form. And what I'll go maybe in my next lecture, so this is a good point to stop, that the dynamical symmetry also means that this part here and this part here also have to commute. So the unitary part, which is responsible for the free evolution, and the dissipated part also have to commute. And what happens when two operators commute? They have a common basis set, right? Now, since these operators are super operators, their common basis set will be operators. So we'll see that the operators, the common basis for the dissipated part and the Hamiltonian part will be these L's, which are called then the jump operators. So these will formulate the common basis, and that seems to be my next lecture. So you have something to expect, and in the meantime, you can ask any questions. Thank you.
It's like in any lectures, the students really don't have much of a choice. If you do not finish it in the first lecture, you can continue on to the next one.
Yeah,
So
it's written. Everything that's here, you can read. So you don't need me.
So I think we will take again a very short break, about